Suction pressure is evaporator temperature. Liquid pressure is condensing temperature. Subcooling is how much liquid are we stacking in the bottom of the condenser. Higher subcooling means we're stacking more liquid. Lower subcooling means we're stacking less liquid. In the evaporator coil, higher superheat means our coil's not as full. Lower superheat means our coil is more full. If you understand those things, you're in really good shape as far as troubleshooting. That's what those things mean, and that is really all they mean. They don't, they're not magical measurements to tell you some other thing. That is what they are. And that can be really helpful for you, because even with subcooling, this is it. Who has heard that, hey, if you want more efficiency, get more subcooling? If you want more efficiency, just add more subcooling. A lot of guys say this, so I'm glad none of you here believe that, so that's good. But what are you doing when you add more subcooling? You're stacking more liquid. When you stack more liquid, you're taking up more of the condensing space with liquid. So you do end up getting higher head pressure, right? But that's the reason why, because you're taking away the effective condensing space by filling that sucker up with liquid. And if you keep going, and we all know this, if you keep adding refrigerant, subcooling 5, 10, 15, 20, 25, 30, 35, 40, right? As you keep going, your head pressure is, that's what's causing the subcooling, is increase in head pressure. Because you can only, the outdoor temperature stays the same, right? Like, you can only get so close to the outdoor temperature with your liquid temperature. So if you're getting more subcooling from that point, more than about 10 degrees, you're really getting it by increasing your head pressure, which is not a good thing. Absolutely, yeah. Yeah, thermal limit on the compressor is kind of that last protection. It means that the compressor is really, really hot, right? It's a major problem. Here's a fun fact while we're on the topic. You guys have capacitors fail here pretty regularly on single stage equipment? Okay, everybody does. It's pretty common. When a compressor capacitor fails, what does the compressor do?
It gets hot.
It gets hot, but what does it do? So like you show up, so you're walking up to a condenser, you got your tool bag hopefully, you're walking up to it, and you'll notice a lot of times the condenser fan will still be running, maybe backwards, but it'll still be running in a lot of cases. You walk up to it, and you hear a and then about 30 seconds later, right? But what's weird is when a compressor goes out on thermal overload because of high head pressure or because of low refrigerant levels, it doesn't do that. You walk up to it, it's not humming at you. It's just off, right? And usually what do you have to do in order to get it running again? You got to cool it down, and it usually takes a while, right? Why? Why, when it's a bad capacitor, does it just reset so quick? It just keeps doing it. When it's high head pressure, the thing is like hotter than a hot thing. I couldn't think of anything. Hotter than a polar bear. I don't know. It's really hot. Because that thermal limit is located in the windings. And when you're locked, when the compressor's locked, which is what happens when the capacitor's failed, it can't spin, right? It can't. Those windings just become little heaters. But all of that heat is contained in the windings, the actual electrical windings, right? And that's what's tripping that limit, and that limit is right there in the windings. It's just right there with the windings. So it heats up real quick, cools down real quick, heats up real quick, cools down real quick. When it's an operational overload, it opened the overload because of something that happened with operation, that whole compressor is hot. The whole shell, everything is hot. You have massive thermal mass. There's a lot of metal, all the steel, all the parts inside. And so when all that gets too hot and trips the overload, it's going to take a while. And that's one of the best ways to know why an overload tripped. If you walk up to a compressor and it's off, and you put your hand on the top of it, don't push your hand on the top of it, just touch it, and it's hot, it's an operational overload. Low refrigerant charge, high head pressure, something like that. It's not an electrical problem. If it was an electrical problem, it's not a capacitor at that point. Right, exactly. Now, you still check the capacitor, right? Like, you still check that. But that's not what it is. It's an operational overload. And that's a really handy thing to know. And one of the things that drives me crazy is when guys show up and they find a compressor that's out on overload. And they go, oh, hey, I got open windings. Got open windings on the compressor. Well, yeah, you do, because the overload's open, right? That's what the overload does, is it opens the windings to common, right? So, of course you have open windings. Touch it. Oh, yeah, it's hot. Okay, well, it was just running then, right? It wouldn't be hot if it wasn't just running. Oh, well, I cooled it down, it didn't reset, we need a new compressor. No, you don't. Just give it more time, right? Because it's hot, meaning it was just running. So it literally, I mean, the odds that it failed just at that moment when you showed up, very low. You just didn't give it enough time. So you can you do the hose on it, you give it 6 hours, 24 hours, whatever, give it time. Odds are it's going to reset. Now, sometimes it's an embarrassing conversation to have with the client because it's like, look, it's not resetting on me right now. We're going to have to come back, but I'm going to run these other calls and then I'll come back and see. But don't just condemn the compressor, because that compressor 99% of the time will end up resetting, and then you can find the cause of what caused in the first place. Because the problem is if you replace that compressor, the problem that caused that to happen to the compressor is still there, and you don't even know what it is, right? So that's a major issue, right? And a lot of times it is a failed TXV, it's flat on charge, whatever the case is.
Yeah, I have experience where a compressor started running backwards, and the liquid line started to suction like it won't.
Yeah, I mean, I guess especially on a rotary compressor, I think that might be more possible. But yeah, it depends on the compressor design. I guess that is feasible. Yeah, maybe. Backwards running compressor heat pump. You designed something new and you didn't even know it. You're an engineer. All right, delta T. So when I first started in the trade, delta T, which is just temperature return, temperature supply, right, was like everyone's go-to. And so what everybody did, it was like one of the only things you measured. And then I learned about all this other stuff, and so I started to hate delta T. Because I'm like, look, it's super variable, there's a lot of factors. But then as I've gone on, I kind of like it again now. Like, it's not perfect, it's a little bit of a sloppy measurement, but when you use it in comparison with these other things, it's pretty good. Now, what I would prefer is that you would use a psychrometer in the supply and the return, because that would tell you a lot more. Like, now you'd be able to know how many BTUs you're moving. That's a better thing, and it's not that much harder. The hole's just a little bit bigger, right? Stick those in. The downside to psychrometers is that they do, like, the sensors are a little more sensitive, they're more expensive, and so I'm still okay with people doing good old-fashioned delta T in and out. But I do need you to know that delta T is a rough look at airflow, kind of a really, really rough one. Because when you have a high delta T, that does tend to indicate lower airflow. And when you have a lower delta T, that does tend to indicate higher airflow. But keep in mind, in a humid climate, a lot of the rules of thumb go out the window. Okay, because the more humid the air is, and we're talking total humidity, so when you start up a unit and it's really humid in there, and that thing is just, you go out and the drain is just raining on you, right, just pouring out water, your delta T is going to be low, right? You're going to see 14, 13 in some cases. Now, it shouldn't stay that way, though. Like, as the house dries out, that delta T should start increasing on you. Okay, and the reason that is because, and again, if this is hard to understand, just remember it's this sensible latent thing, okay? We're not going to, again, with this group, that's a little basic, but I'll just cover it quickly. Sensible means heat that goes towards changing temperature. Latent means heat that goes towards changing things from liquid to vapor, right? Or vapor to liquid. There's two different types of latent. There's the latent that happens inside your coils, inside your condenser and your evaporator, right? That goes to the changing, the boiling of the refrigerant or the condensing of the refrigerant. But then there's latent of condensing water on your evaporator coil, right? And those are two completely different things, right? They're not the same. They're both the same in the sense that you're changing things from vapor to liquid in both cases. But when you're condensing water on the outside of your evaporator coil, everybody with me right now? When you make water on the evaporator coil, when it drains outside, it's because you changed it from liquid water, from vapor water to liquid water on that coil. Coil's below dew point, it's condensing on that coil. That energy that goes towards doing that does not change the temperature of the air. It only goes towards that effect of changing it from vapor to liquid, which means that in markets like ours, a lot of the energy that air conditioner is spending is being spent towards changing vapor water to liquid water. Make sense? And so that energy that's spent doing that does not show up in our delta T. That's why in other markets they're like, oh yeah, 20, 22 degree split, that's good. And in our market we're like, ooh, we don't usually get that, right? When it's humid, when it's really humid, we get a lower delta T, and that's okay. But it does mean that our systems don't get the same overall capacity in the sensible sense and the changing the thermostat sense, because a lot of that energy is going towards changing it from water vapor to liquid. Does that make sense? But that's not the same as the latent that we talk about inside the system. Inside the system, we're talking about latent, and we're like, you know, how the evaporator is like the same temperature all the way through, like we talked about evaporator temperature. That's that kind of latent. It's hidden because the energy is going towards boiling the refrigerant inside the tubes, right? This is not actually that complicated, but it's very hard to explain in a way that people grasp. The point is...
So the latent, what I understand over here is that latent is the most difficult heat transfer.
Correct.
Because not only that, it's inside, it's actually inside of, it's heat that is absorbed by everything inside of it. Right?
Yes. Yes, and that's a really good point.
Latent just means hidden.
Right.
So that was the big revelation for me. It's just like, oh, okay. It doesn't really, it's not like special to water.
No.
Which is kind of what I always thought before. I
No.
was like, oh, it's like when you take water from the air and you turn it into liquid, like that's what latent is. But it just means that like you can't see it.
Right.
Basically.
And in this case, it means specifically that you can't measure it with a thermometer.
Yeah.
That's all it means. Your thermometer is useless. You know, your weak thermometer tools are no use to us here with latent. I don't know. I was making up a weird fantasy joke there. I don't know what happens. It was Star Wars? Okay, good. Yeah, and again, like, and this is a really big thing, kind of to what you were talking about that I want to mention quickly. In our market, what people don't realize is, and you see this happen, you go into a house, it got really hot in the house, it got really humid in the house. A lot of times people open the doors because they're trying, doors and windows because they're trying to, and so now you walk into this house, you fix the air conditioner, you close the doors and windows, they call you back 3 hours later, man, this thing is not cooling. It is not dropping the temperature in this house. Have you guys ever had that call before? Yeah. And this thing is not working. Right? And there's for a couple reasons, because it's not blowing as cold as I'm used to, right? Well, no, it's not, right? It's not for two reasons. It's first not because it only drops the temperature of the air going in. So if the air going in is 90, then it's only going to drop it so much. It's not going to be that cold. But the second reason is the air coming out is not going to be as cold when the air is very wet, because a lot of that energy is going to making the air less wet. But here's the other thing that you were saying, and this is really, really important to understand. All the stuff in the house has absorbed all of this moisture, right? It's a really weird thing about water. Is so weird. I could literally do a week-long class like this just about the water molecule, and I am not kidding. It is an insane thing. The water molecule has this negative and positive polar side, and it attracts to itself, and it gets absorbed in stuff. But here's the weird thing. Water is absorbed into stuff based on relative humidity in the space. That's not true about other ways that water moves. It actually moves based on absolute humidity, absolute moisture content in a lot of cases. But in the case of going into stuff, it's based on relative humidity. So if you let a space get up to 80% relative humidity, that means all the stuff in the house, all the wood, the furniture, the bedding, everything has absorbed all of this moisture. And now when you start drying the house out, it starts giving it up again. But it takes for freaking ever for that to happen, right? So it's really important that you know that, and that's the reason why in a lot of cases it's like, man, why isn't this house not cooling down, right? It's taking forever to get to temperature, right? Because it has to do all that work.
And that is why when your sites in a unit don't just measure space, measure everything, target everything that is in that.
Correct. It is, and that is weird. Like if we were to design a load calculation method just for hot and humid climates, we would do it completely differently. And you would really just look at equipment. You would look at equipment totally differently than we do too. And this is a totally off subject topic, and so we're not going to do all of this. But it's really interesting. And to your point, what he's saying is, when you think about the mass inside of a building, like all the stuff in a building, if there's more stuff in that building, you go to a hoarder's house, somebody who's like packed, floor to ceiling with crap in their house, and you let that house get really humid and it's been that way for a couple days, it's going to take forever to dry that out. Like, it's just going to take forever. And so to know that as a technician is an important thing to know. You can't use tools to tell them how long it's going to take. Like, no, we don't have access to that. But being able to say, like, hey, there's a lot of stuff in here, And this is going to take a couple days to dry out. Now, you have to do your due diligence and make sure that the equipment's working properly, right? We have to do that part. That's important. But just knowing that this latent effect is really, really big. And that's the latent of moisture in the stuff, moisture in the air, turning it into water on the coil. There's a lot of energy that's involved in that, okay? That's on the outside of the coil. You get that. And the reason I'm saying this is so when I say the word latent, I could be talking about that, or I could be talking about latent inside the coils, the changing, the boiling and condensing of the refrigerant inside. But those are two different things. Make sense? Language is tricky that way. Go ahead.
Oftentimes when you understand the relationship between how much how much humidity you have inside affects the delta T. For a lot of people that like to take delta T all the time, especially the newer guys, it can be, there's a lot of factors, right? But it can be an indication that you have either an airflow problem, if it's not set up right, you got way too much airflow, and or you have a humidity problem.
Right.
Doesn't mean that. It can be normal, it can have the doors left open all day with
Right.
off. But it definitely is worth investigating because
Right.
humidity problems are probably one thing that gets left unchecked and unconfirmed.
Yep.
Way too long.
And so you guys, if you hear what he's saying, like remember, you all are my people, okay? Like you speak the language of, I speak the language of all of you, which is our problem is moisture, right? In my town, it's moisture. When people call me, when people text me, when people send me emails because they watch my videos, it's always, hey, I've got a mold problem. Help me with my mold problem. I've got this moisture issue. I can't figure it out. All the time, all the time. And so for most of the country, people will say, yeah, 20, 22 degree delta T, that's about right, right? Most people say that. Forget those people. They don't know what we're dealing with. When we're measuring delta T, we're doing it for a different reason. Yes, it tells us a little about airflow, but it also tells us a little bit like, hey, what's going on here? My delta T is low. Everything looks like it's working right, moisture. This coil's dealing with a lot of moisture. And that's where, like, using your senses as a diagnostician is huge. We're going to talk about that quickly here. Like, if you walk up to a system and you look at the drain and it's just pouring water, there's a lot of moisture is entering that home, right? If you're there for a maintenance and that sucker's just pouring water, there's a lot of moisture entering that home. It might not have anything to do with what we've done, but just seeing that is an indicator. Now you do your delta T and it's like, yeah, my delta T is low. Let me grab my psychrometer. Let me look here. Oh man, yeah, 75% relative humidity in this house. Why is this happening? What's going on here? Right, or even 65%, whatever. It says, what's going on here? This is an issue. This is something we've got to deal with. Go ahead.
Yes, I've got at least 3 online guys, DIY, whatever, and they're bragging about 30 degree delta T, saying,
Right.
see, this is better than 20.
Right.
Oh, no, that means you got an airflow problem.
Right. Means you got low airflow. Right. And for those of you who don't get why that is, when you move the air slower over the evaporator coil, it gets colder. But that's all that is, right? So lower airflow means colder air. And that's where when we do these things together, and then you add in things like static pressure, you add in things like using your psychrometers and doing delivered capacity, you can kind of build a story. And that's what you're doing. Back to what Matt said, you're building a case. What's going on with this house? And when you start to look at every house that way, not just every once in a while, not just the problem houses, when you start to look at every house that way, like, hey, let's figure out what's going on here. Like, there's a story on this house. You can start to solve really big problems that people don't even know they have. And now that's good for them, because now they at least could solve it if they want to. And it's good for the business, because you can charge a lot of money to do that, right? Because other people aren't going to do that. Go ahead.
I've seen where just by leaving the thermostat on,
Yeah, there you go.
as when you go inside, all the grills have more.
Yep.
buzz, and they say, what is happening?
Yep.
You can smell it because when the unit cycles, the coil is wet, and then the fan is moving all this air that's full of moisture.
Yeah.
throughout the space.
Yeah, the thing to do is to take a Sharpie and to draw an arrow to the on button with a Sharpie on the thermostat and write no, exclamation point. I was joking, don't do that. Yeah, but again, a lot of people misunderstand why that is though. Okay, so again, we're doing this random kind of, but these are all the things we're going to talk about anyways. This is okay. Why is putting the fan in the on position a problem in a humid climate? Re-evaporating moisture off the evaporator coil. That is the reason that most people say, and that is true. That is a big part of it, but that is not the only reason. In fact, based on testing we've done, it is not even the main reason. And this is kind of cool, because when you have a house that has a problem when the fan is left in the on position, it also means that they have a problem, period. It's being made worse by the fan being put in the on position. And that is the idea of imbalanced airflow and ventilation. So when you have, because what's happening when you put the fan in the on position? This is not a trick question. What's happening? Blower's running all the time, right? So the unit's always moving air. So in most cases, the reason why that's causing a problem is because when the system's always moving air, the issue that happens whenever the system is moving air with imbalances and pressures is now happening all the time, right? So if you have leaky ducts, if you have leaky envelope, if you have imbalanced return in supply in certain bedrooms, when people shut the door, it creates pressure drivers. So again, and we're going to do some of this later today hands-on, if you have a case where you have ducts leaking in the attic, right? Let's say it's a supply duct that's leaking in the attic. Well, now, what happens to the occupied space? What happens to the pressure in the occupied space? It's under negative pressure, because you're losing some of your positive pressure. It's not going back into the space. So now, this whole occupied space is under negative pressure. And if it's in on position, that's happening all the time, right? It never stops being under negative pressure, which makes your moisture problem worse. Pulling air in from everywhere, right? From can lights, from doors, windows, everywhere. It's pulling it in from outside, right? In this market, where's the worst place for air to come into the house from? The attic. If you ever take a psychrometer, or hygrometer, or whatever, and you go and look in the attic, go up near the peak of the attic, and look at what your dew point and your relative humidity and your total moisture content is of that air. It is crazy wet air, right? Now, when you create negative pressure in the house, do you ever have people who have can lights in their houses here? You know, overhead lighting? Have you seen those, how well those are sealed in most cases? Not very well in most cases. Around the boots and cans, often not sealed very well. And so when now this space is negative, and attic air is pulling in around those cans and around those boots and around everything, what happens? It hits that space, hits those cold temperatures, condenses, mold crazy. Right? And you see it. I mean, like the house we're staying in, the ductless system, you can see they're doing their best trying to clean it. But you look on the outside, unsealed hole going in through the wall. Look on the inside, and there's just mold just creeping out of behind the unit in all directions. It's just creeping out, right? And that's because air's coming in. And again, when the fan's in the on position, it's worse. Because now air's coming in all the time, right? Infiltration, right? That's the word.
Three units that are positive, right? Some inside the attic is just creating this positive space inside the attic. How does that, what do you think, how that affects the inside?
It makes it worse, right? Again, every time you're putting air or taking air from somewhere that's not inside the house, you're affecting the pressure in the house, right? So if let's say I'm sucking in air from the attic, what does that do to the pressure in the house? Makes it go positive. So it makes air leak out of the house, right? Every time I'm doing the opposite, I'm leaking supply air in the attic, what does that do to the house? And that supply air could be from the cabinet, it could be from the duct, it doesn't matter where it's from, it doesn't matter. If it's leaking in the attic, now what's that doing to the space? It's going negative. Where's that air coming from? Everywhere, and a lot of it's coming from the attic. A lot of it's sucking in from cans and window, all over, right? Let's think about this. Somebody has, rich people really love to have gigantic range hoods. They never cook. They never cook in their kitchen, but they like to have really big range hoods. And then anytime they do decide to cook, they turn on this 1,000 CFM range hood. Where does all that air come from?
Outside.
Outside, attic, everywhere, right? And what does that carry with it? Tons of moisture.
So back to the training. So we selected this equipment, right? And we put it inside the attic. Should we be aware of if the attic is sealed? Because these cabinets are positive, so it's always making the attic positive.
Sure.
So does that affect?
Well, they're only if they're leaking. Only if the cabinet is leaking is it going to make the attic positive.
Only if that?
Only if the attic's leaking.
The timeline, they're designed to leak a little bit of air. They say it's to keep it, conditioner on the unit, keep it positive so you can the air being pulled in, which is by design.
No, that's a bad. Yeah, I mean, if it's in an indoor closet, that's not the worst thing. That makes some sense. But in an attic, no, that's a bad. I didn't know that. I didn't know they said that about that. But yeah, that's not a good design. Again, rule of thumb: 16 to 22 degrees. But again, you got to know that's a 400 CFM per ton calculation in more of a normal climate. In your climate, you're going to typically be a little bit lower, and you can compensate for that a little bit by running a little lower evaporator airflow. So you're going to get, as you get that evaporator airflow lower, then that's going to kind of compensate for the fact that you have more moisture. But again, the thing I want you to know, when you have a low delta T, that could be due to a problem, but often it's going to be just due to the fact that you have high humidity, right? Make sense? You were going to say something.
It's still something you need to investigate. I mean, if
Correct.
you're over 60%, definitely if you're 65%, you need to do something.
Correct.
60-65%.
Relative humidity.
63%. You're really at 60 because if you're 60 in one location, you're 65 in another.
Correct.
So really,
Yeah.
If you're above 60 anywhere, you need to bring it down.
Yep. Yep, for sure. Did you hear what he said? If you're above 60% in the house, you need to work on that because it's going to be a problem somewhere in the house, and from an isolated standpoint. It should be a priority, and I agree with that. Sometimes it's hard in some houses, and we're going to talk about a little bit later some of the things to look for. All right. Isolation diagnosis is making a hypothesis, like I think this is what's going on, and then using a method to isolate that hypothesis. Hypothesis just means they came up with a theory of what's going on. And so you come up with a way to isolate and prove or disprove that theory. Okay? In electrical, this is really, really handy. Right? I'll give you one of the most common ones. You have a compressor that you're convinced is shorted. Okay? Grounded compressor. Everybody's seen that before, right? So one of the best ways to make sure that you know for a fact that it's the compressor and nothing else, because you knew that it was grounded because the breaker tripped, right? And you probably reset it and it tripped again. And then you ohmed out the compressor to ground and you said, okay, I'm convinced that this is shorted. But sometimes it's not that straightforward, okay? What I want you to do is take the plug off of the compressor or the terminals. Make sure if you have terminals, take a picture so you put them back on right again. Take them off, isolate them, put them to the side. They're not going to short on anything. Put the top back on, flip the breaker on. Now if everything else works and the compressor is isolated out, you have now proven your hypothesis. Your hypothesis was that it was the compressor that was shorted, so you eliminated the compressor. Now you know. And for more experienced guys, right, you're like, well, I just use my ohm meter and I can tell. I'm like, that's fine, right? I get that. But for junior guys, trust me, you want them doing that test. You don't want them using the weird Subco mega ohm meter with the red button that says bad and then the compressor's not actually bad or any of that kind of stuff. You don't want them doing that. You want them doing what I just said. That final isolation. Prove it that it's just the compressor and nothing else. Make sense? That's an example of isolation diagnosis. But there's a lot of others, right? So I think you have an evolution controller. I think the controller's bad. Take the controller off the wall, bring it to the air handler, and wire it up right to the air handler. Right there. I just want to see, does it work now? Because what does that eliminate? What does that isolate? That entire conductor, right? Now, it doesn't isolate the conductor from the condenser to the air handler, but that would be hard to do. So this is at least you're eliminating that possibility. That's what I make the guys do when they tell me, oh, it's a bad controller, it's a bad board. Do that at least, right? Because often it's like, oh yeah, it worked. Well, right, process of elimination, that's what you're doing. But you're doing it in a so when I talk about isolation diagnosis, it's not a fancy way. Like, I don't like it when people immediately go to like a fancy tool or a fancy process when there's a simple way to do it, right? It's the same thing with like ECM motor testers. Who here has an ECM motor tester, Gentech or one of the others? Okay, most of you, good. Simplest thing in the world, right? Plug, clip, does it run? No, it doesn't. Okay, bad motor, right? That's an example of isolation diagnosis in action. You don't have to overthink this. It doesn't have to be complicated. Keep it really simple. The other thing with isolation diagnosis is before you even make a hypothesis to be able to do isolation, always do a thorough visual inspection. Always, right? So if you're dealing with a low voltage short, it drives me crazy when guys immediately start disconnecting wires all over the place. It's like, oh, please stop. Like, go outside, look, control wire, track it with your eyes. Feel it all the way underneath. Okay, there's no splices, there's nothing weird. Look down in the condenser. Okay, is anything rubbing anywhere? You know, anything touching that could be, and often I'm going to pull the top off and just move the wires around and just see. I'm going to pull the quarter panel off of the side panel. I'm going to go in there, I'm going to look. Okay, is there anything? If it's one of the ones that often have shorted contactors, you guys still running into the shorted contactor coil issue? In that case, you can either eliminate it, you can just disconnect it and then retest, or you can actually ohm out the coil if you kind of know what you're looking for there. But you're basically doing visual inspection and you're looking at the most plausible causes before you do anything else. We've all learned to do that with capacitors, right? Like you walk up to it, compressor's not running, you can hear it's not running, you pull the panel off, you look, top's bubbled, bad capacitor, right? We all learn to do that. That's a visual inspection, it's a practical inspection. But the same thing is true with the thermostat. Like you walk up to the thermostat and you see that it's like some brand. Do you have hardware stores here where people can buy thermostats? Like homeowners can buy them? And you walk up and you look and it's one of those. Did you replace the thermostat? Yeah, I did. And oh, okay, okay, yeah, right. And you pull it open and right, they hooked blue to the B terminal or something, you know, something obvious like that. And so it's just that practical. Once you get to the point where, all right, I've done all my practical visual inspections, now I want to do isolation diagnosis. And again, some of this has changed over the years, but I want to, let's see what I got here. Yeah. But I want to cover it with low voltage, because this is one of the areas that guys struggle the most. They struggle with low voltage. Now, again, if it's a communicating system, it's a little different, right? You have to follow the best practices. We're going to talk about communicating systems, VRV, VRF tomorrow. Jordan's coming in, and we're going to really cover that more in that section. But we're going to assume that it's a 24-volt system that you're working on, okay? And you show up and you have the dreaded blown fuse, all right? Now, first off, what makes a fuse blow? Short circuit, amps. Okay, now quickly, I want to just, because I did this with the apprentices yesterday. Could be. I want to do a couple things with you. The first is, make sure that you don't confuse the terms short and open, okay? So I want you to raise your right hand and repeat after me. Just kidding, I don't want you to do that. A short is when something is happening that should not be happening. Okay? An open is when something is not happening that should be happening. Okay? The problem is, at a very young age, we learned from our grandparents and our parents and everyone else that short just means anytime something weird's happened with electricity that we don't understand. Right? It's like the TV's acting weird. Ah, it must have a short in it. The refrigerator won't run. Ah, it's a short, right? We just say it too often and it becomes a meaningless word. But a short is a very particular thing, right? A short is anytime there is an undesigned path, right? And what causes a breaker to trip or a fuse to blow is current that is higher than the rating of that breaker or fuse. Make it simple, right? If you have a 30 amp breaker and it's tripping because the circuit is drawing more than 30 amps, right? If you have a 5 amp fuse that's blowing, it's blowing because the circuit is drawing more than 5 amps, right? Who's here from yesterday's apprentice section that we did? Raise your hand, everybody who was here. Okay, so these guys are going to teach you something. A 40 VA, if you don't know the answer, don't say it. I want them to get it. A 40 VA transformer. Okay, 40 VA transformer. Everybody's seen that before, right? 40 VA. What's VA stand for? Volt amps, okay? So how many amps can you put on a 40 VA transformer on the 24 volt side? How many amps? The apprentices know the answer to this. These guys are brilliant. How did you come up with that how did you come up with that magical math? 40 divided by 24. Man, these guys are good. Give these guys a raise. Just kidding. I didn't say that. 1.66. Okay, now this is kind of an interesting thing. So, what size is the typical fuse? Amperage? 3 amps. But that transformer can only handle what? 1.66. So is there a case where the transformer might blow and the fuse not blow? The transformer might fail and the fuse not blow? Yeah, there is. And it's kind of like in that range. Is that likely? Probably not. But it can happen if you have high load, like if somebody connects a UV light in addition to the regular stuff on one transformer, right? That could happen. It's possible. So just understanding that's kind of a neat thing that I thought, well, I mean, I like it. It comes up at times. And you run into some systems that do draw high current. Some multi-stage pieces of equipment that draw higher current. And those are often the same pieces of equipment that make fancy thermostats fail. So when Nest thermostats like keep failing on you eventually, it's because that Nest thermostat has like even a smaller fuse in it, like a 1 amp fuse or something goofy like that. And so when you draw a little higher current, they failed. So when Nest first came out, this was like a massive problem. We just had them failing all the time because of that issue, that internal stupid fuse that they had. So if you have a fuse blowing, you know that it's over that current. There's multiple things that can cause it, but generally it's a short. Now here's another thing. If you have high current, does that mean that you have low electrical resistance or high electrical resistance? Low resistance. Low resistance equals higher current. I'm glad you all knew that. That's Ohm's law, right? That doesn't sound right to us, okay? But think about it, all right? Less resistance to flow means more flow. Less resistance to current means more current. So right now, in this room, what thing in this room has probably the lowest operating resistance? Ice machine compressor, probably. The ice machine compressor probably has the lowest operational winding resistance right now. And that's, if you've ever noticed, have you ever ohmed out compressor windings? Like take an ohm meter, ohm them out, a working compressor? Anybody ever done that? It's like low. It's like, most cases, like 3 ohms, 1.5 ohms, 4 ohms, in that range, right? Like that's not very high ohms. And that kind of makes sense, right? Now if you do the math, it's like, man, this thing should be drawing a lot of amps. Yeah, that's locked rotor amps. Once it starts running, then it drops, and we're not going to talk about that right now because that's more complicated. But so it is the resistance being too low that causes the current to be high, right? I'm going somewhere with this. So when you have a wire that's touching ground or like not wired right or something shorted, it means that the resistance of the path is too low. Make sense? The resistance, and that's what a short means. It's taking a shortcut. It's not going the long way around. It's taking a shortcut. The electricity is taking a shortcut back to where it came from, the other side of where it came from, and it's not going the whole path it's supposed to go. That's all that means, right? So when we want to troubleshoot a problem with 24 volts or any sort of control, we want to find a way to isolate the most probable circuits. All right, so here's the first thing I do. And you can use like some of these like 3 amp little popper fuses and stuff. Some of them don't work very well. There's a couple that work okay. You can just keep blowing fuses if you want, as long as you have plenty of them, you know, and your boss is okay with that. But the way I typically do it is I notice and observe when the fuse blows, if I can. So I'll first look, I'll do the visual inspection, I'll do all that. Then I'll put the fuse in. So I'm going to waste 1 fuse this way. And I'm going to have everything off of the thermostat, and then I'm going to energize 1 circuit at a time. So I'm going to start by energizing fan on. Fan on. Does it blow? Does the blower come on? Blower comes on. Which circuit's okay now? G. I know G's okay now, right? So now I actually know a couple circuits are okay. I know R is okay, it's not shorted, and I know G is okay, it's not shorted, right? If I put the fuse in, it blows right away, okay, it's R, right? If I had it off and isolated. All right, now we're going to turn on Y. And again, in your market, that's all you've got. You don't have O, you don't have W, you don't have anything else, right? It's a piece of cake. So now I'm just going to make sure Y, oh, Y blows it. Okay. I know it's in the Y circuit somewhere. Now, it could be the contactor. It could be a pressure switch. It could be the wire going to between the thermostat and the air handler. It could be the thermostat between the thermostat and the air handler and the condenser. Those are really the places it could be.
Just looking at the chart, number 2, is that a reasonable
Yeah. They do make them. Little popper is the most common one. And theoretically, it's a really good idea. The problem is that a lot of times it doesn't trip, and then it ends up frying your transformer. And so theoretically, this is a really good idea. There's another one, the other one I can't, Short Pro. And that one works a little bit better, but it works differently. So it just sort of gives you an indication that there's a short. It's been a while since I've used one. Do you have one?
Yeah, it lights up.
Yeah.
LED, which short, it'll light up the LED and drop it.
Drop it down, yeah. Yeah.
I've got one that I've never had a problem with. It's never blown a transformer.
The little popper on you?
It's not a little popper. I don't know.
Okay. There was just, I used it for a while and we just kept burning up transformers, and that was not, I didn't stick with that. But that idea is great. If you can use a resettable one, like Short Pro or like a you know, they make them, and I would definitely use the 3 amp version. That helps you from wasting fuses.
Bryan, have you ever done it where you put, if you can't find the short, where you'll put a fuse on each individual wire? Yeah, have you ever seen people do that?
Yeah.
Yeah, no, you can do that. Yeah, I mean, and that would work. I mean, if you have something like Short Pro, that would probably make it a little easier. But all you're trying, there's so many different ways you can do it. What you're trying to do, though, is what I don't like people doing, and I see them do it all the time, is they immediately disconnect everything from everywhere. And it's like, don't, like, why? You know, just use common sense first, and then just do one circuit at a time. And it's going to save you a lot of time and heartache, especially in your market where there aren't really that many conductors anyway, right? So now you go inside and disconnect, air handler disconnect, condenser and disconnect. You're disconnecting everything. Just work your way through a process of elimination.
Yeah, I had a similar situation where it was just a communication wire that was bad. But, you know, because overthinking, you know, the diagnostic, it took a long time to actually show me that it was a 4-4 communication wire. Who had been, so it only uses tools that they can do. So we can obviously look and see where 2 wires were used at one time, took them out and using them.
Right.
So now I'm getting too technical, going through the thermostat, looking at codes, all
Right.
that. Unnecessary.
Right, right.
Common sense.
Yeah. And what he's saying is, if you guys didn't catch that, what he's saying is he went to a communicating system and he saw where they had originally used 2 wires and then they abandoned them and used 2 different ones. You kind of know the story there, right? You can build the story that they already abandoned 2 conductors which were failed, and if there's a couple failed conductors, shorted, whatever, in a bundle, in a cable, it's very likely that the others are too. And sometimes you can use other ones to get by, but again, the right way to do it is to take and isolate all of the conductors on both sides then, and check them to each other and check them each to ground. But again, that's where the limitations of an ohm meter come in, right? That's where it's kind of like when you have a megometer, now you can check it under higher voltage and really see if any of them are compromised, which is handy. If you don't have that, then at that point, you're kind of like, all right, we're just going to have to replace this conductor, you know?
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.